The universe keeps a secret pattern hidden inside apparent randomness. That pattern explains how galaxies organize and where structure appears. Picture a broad starfield, rim light on distant dust, and faint filaments stretching between glow points. Hidden order means a statistical regularity that repeats across different places. You should care, because those regularities shape the galaxies that host planets and life. Gravity amplifies tiny differences and sculpts matter into larger forms over time. Quantum fluctuations add random noise, and symmetries limit possible outcomes as well. Observers count and compare patterns using statistical measures to reveal consistent trends. For example, the cosmic microwave background shows tiny ripples precisely matching theoretical expectations. So beneath apparent chaos, there exists layered order we can test and refine. A sky survey looks like a scatter of tiny lights across darkness. Hidden order here means the statistical arrangement of galaxies across space and time. This matters because those statistics tell a story of how structure grew from early fluctuations. Gravity causes denser patches to attract more matter and amplify differences as time passes. Dark matter behaves like invisible scaffolding and guides ordinary matter into filaments and nodes. Astronomers compress these patterns into power spectra and correlation functions to compare models against observations. Large surveys have counted millions of galaxies across billions of light years and cosmic epochs. Those numbers align surprisingly well with simulations seeded by the early universe conditions. So noisy galaxy maps hide robust statistical rules connecting early physics to present structures. Stand near a single galaxy, and motion appears surprisingly organized like clockwork. Local order refers to predictable dynamics at the scale of stars, gas, and dark matter. This matters because those motions reveal unseen mass distributions and merger histories. Conservation of angular momentum keeps stars orbiting in flattened disks and sculpts spiral arms. When galaxies collide, tidal forces pull stars into long, coherent streams stretching across space. Gas cools and flows, forming stars preferentially along dense planes and filaments inside the disk. The Gaia mission mapped billions of stars and found dozens of tidal streams around our Milky Way. Each stream is a fossil record of a shredded dwarf galaxy, and it reveals timing and mass of the encounter. So nearby stellar motions look messy at first, and yet they encode a reproducible dynamical order. Cosmic structure often builds itself in nested shells and flowing streams across sizes. Nested order means similar architecture repeating from small to large scales within the universe. You should care because identical physical rules operate across those scales and connect phenomena. Gravity collapses matter into shells, then into filaments, and finally into dense nodes that host galaxies. Pressure, magnetic fields, and feedback from stars modify collapse and set characteristic radii where structure appears. Numerical simulations reproduce shells and streams that match observational surveys in X-ray, optical, and radio bands. For example, one cluster study traced coherent inflows stretching millions of light years toward a central galaxy. Those inflows concentrate gas at predictable radii and trigger star formation bursts in measurable ways. So nested shells and streams act as a repeating blueprint that links small-scale physics to large-scale patterns. On the largest scales, the universe forms a vast filamentary network we call the cosmic web. The web is the interconnected pattern of matter that determines where galaxies form and grow. This matters because filaments funnel material into nodes and thus control the pace of galaxy assembly. Dark matter collapses into long strands under gravity, and baryons follow those wells to light up as galaxies. Deep surveys reveal filaments spanning hundreds of millions of light years that connect massive clusters. Density maps make these filaments visible as elongated strands, channeling matter inward toward cores. Simulations seeded with early universe fluctuations reproduce similar web geometries across cosmic time. So the cosmic web is a grand ordered scaffold underneath what otherwise looks random in the sky. Turning faint signals into reliable patterns depends on precise measurement and careful statistics. Measurement means converting photons into numbers while quantifying uncertainties at every step. This matters because weak patterns easily hide beneath instrument noise and survey biases. Telescopes collect light, and detectors imprint subtle systematics we must remove through calibration. Analysts correct selection effects and apply statistical techniques like stacking, and cross-correlation to boost signals. For example, researchers stacked thousands of galaxy clusters to detect microkelvin-level distortions in the cosmic microwave background. That tiny signal agreed with theoretical predictions and strengthened the pattern interpretation substantially. Better measurement turns messy observations into robust evidence we can compare to physical models. So careful experimental design and statistical care are essential for revealing hidden cosmic order. Often complex cosmic patterns arise from surprisingly simple mathematical rules and symmetries. Simple rules are scaling laws and symmetry constraints that reduce chaotic variability into predictable trends. This matters because a few dominant processes are easier to test and falsify with data. Turbulence and gravity commonly produce power laws that hold across many orders of magnitude in size and mass. For example, the mass distribution of interstellar clouds follows a power law across several decades. When simulations include only a handful of physical principles, they reproduce these distributions remarkably well. That convergence suggests dominant processes sculpt complexity into repeatable outcomes across scales. So simple mathematics often explains a wide range of cosmic behavior we observe. Deviations from expected patterns serve as stress tests for our understanding and prompt progress. An anomaly is an observation that significantly departs from predicted statistical behavior. This matters because anomalies can reveal missing physics or expose data issues requiring correction. Examples include odd galaxy alignments, unexpected rotation curves, and mysterious fast radio bursts that defy easy categorization. Some anomalies disappear with improved data quality, better calibration, and refined analysis methods. Others persist, and they motivate new surveys, instruments, and theoretical frameworks to explain them. For instance, a set of unusual galaxy rotations challenged simple dark matter interpretations and triggered targeted follow-up studies. So anomalies are the sharp edges that either break or strengthen our hidden order models. The hidden order we opened with the hook produces practical payoffs for science and technology. Recognizing patterns improves cosmological parameter estimation and optimizes telescope survey strategies. Better models sharpen predictions about where rare events occur and how structures evolve over time. This matters because directed observations save costly telescope time and accelerate discovery. New instruments and larger simulations continually refine the layered picture and test its limits against anomalies. Upcoming surveys will map billions more galaxies and push these statistical tests to new precision. Keep watching research progress and expect surprises that either fit the pattern or force us to rethink it. So the net picture is layered order embedded within apparent randomness, a testable and useful discovery.